I'll be talking about three things here. I'll be talking about radio models and physical Mac solutions for vehicular communication. I'll be talking about simulation of cooperative platooning using the ITS stack. And finally, I'll be talking about a 5G enabled emergency braking application that also has a demo associated. So starting with the first topic, and this is work mainly carried out by our colleague from also ISEP, Cister ISEP Remir Robos, also with some other students. So we've been working on multiple input, multiple output line of sight channels or communication systems, more correctly. Also, with considering round reflections, as we see on this um, image over here where we are considering the possible reflections of the wireless signal on the floor when we have a communication between two vehicles of a platoon, right? So we also have analysis of V2V channel statistics when there's double scatterer interaction, also a new geometry-based stochastic channel for the Manhattan grid. Um, Moving forward, we have also on this topic an analysis of interplatoon communications for the emergency brake collision calculation, authentication and security at the between the communications of the platoon through a physical layer using the special signature of the platoon. And also we are performing using AI to perform channel prediction using AI again. So this is work done also using some real data that we through interactions with partners. A final point is also the implementation of the successive interference cancellation non-orthogonal medium access with retransmission diversity, also which I believe is being also implemented by some partners. Also, a lot of this work gains from synergies with another work, which is with another project, which is Insect, also of which also Cister is a part of. So moving forward to the second topic, I will talk about the work that has been also ongoing at Cister for some time, which is cooperative platooning. So in this case, we ask the question, can we use these cooperative awareness messages, which are essentially messages defined by the ETSI ITS standards, which essentially are about each car sending periodically, let's say every 10 times a second, their position, speed, and direction. And by having all cars sharing this information, again, at 10 hertz frequency, other cars can be aware of what's around them and can have an idea and plan for avoiding, for example, collisions or for cooperative maneuvers. So, but in fact, the standards actually say that the rate at which we transmit these CAM messages can vary with respect to some kinematic threshold. So if I'm steering too fast, if I'm accelerating too fast, the frequency of these messages can actually increase or decrease. And our colleague Enio Filho was curious, okay, if we change the values of these thresholds at which we should send messages, let's ask two questions. So does the platoon still operate correctly without any flaw? And are we creating too much noise in the network by just sending a bunch of messages that are unnecessary? So it turns out this is not a very, does not have a straight forward answer. There's a sweet spot in between the number of messages that we sent and observing that the platoon is performing correctly, both in terms of the distance error of the vehicles between themselves, so the error between the intended distance and the actual distance that we are observing, and the error between the angle, the steering angle that we want and the one that we are observing. So all of this comes into play in terms of having a platoon that is purely, in which each follower is purely listening to the CAN messages of the car in front and reacting to those. So no, let's say, proactive communication between them, just receiving the CAMs and actuating in response to that. And so by varying the thresholds, the kinematic threshold values at which we are going to send the messages, again, we find that there's a particular profile where we are sending not either too much nor too little messages, and we are still striking a good balance in terms of the performance of the platoon. So, and there will be more details on journal paper that we had on this. A final topic on this is the 5G enabled emergency braking. Essentially, we have a platoon that is approaching an area where there's a pedestrian. However, the vehicles cannot see the vulnerable road user. However, we have some communication infrastructure, either 5G or 802.11p, a local edge network, and a camera that is able to observe the pedestrian. So what happens now is that the object node detecting the edge node performing object detection will detect that there's a pedestrian ahead, and this message will be using the video stream from the camera. And in the second step of the scenario, we will have a message being sent to the vehicles so that they brake in time and no collision happens, right? So we had the first implementation of this same scenario with 802.11p. So we had a camera, an edge node, and a roadside unit in a small test bed. So we can see that we actually implemented this in our laboratory where we have the roadside system, a makeshift obstacle, and then our scale vehicle, which is a robotic a remote controlled car, but in this case, it's navigating autonomously using camera and LiDAR, and it's also equipped with an 802.11 onboard unit. And so we were interested in measuring the end-to-end delays since the camera observes the pedestrian until a brake command reaches the vehicle actuator. So going from the roadside infrastructure until reaching the vehicle and actually telling the vehicle to stop. And so we observed that in this very controlled scenario, we were getting values between 45 milliseconds and 72 milliseconds. Of course, these are highly optimistic. We did try to induce some interference, although we were not very successful at that. So this is really something definitely that we will revisit. Yeah, and so this definitely tells you that there's not a fixed value. Actually, it will be a distribution. This latency will follow some distribution that we need to further clarify. And the final slide that I have, in which is the evolution of this, is when we have not one car but two cars, and now the information is being sent not via a local roadside unit, 802.11p roadside unit, but actually from the 5G network. And in this case, we see the front vehicle. Both vehicles are equipped with onboard units, and the front vehicle actually also has a 5G network. And so we are replicating the same scenario, but instead of using a local roadside unit, we are actually using the commercial 5G network. And that's it for my side. Check out our demo.